Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to find the relative abundances of isotopes in a particular element. So let's get into this. So in this problem we're given, they're asking, or they let us know that the element chlorine has only two naturally occurring isotopes. You have Cl35, and they give you the atomic mass, or the molar mass. In this case, 34.9688 or 34.96885 grams per mole. And then they give you Cl37 or chlorine 37, and the molar mass is 36.96590 grams per mole. And then they ask, determine by calculation the relative abundances of the two different isotopes. Okay, so what you want to keep in mind is we need to understand the distinction between percent abundance and relative abundance. They're very related to each other. So, and that's going to help us out. And if you know the equation for how to find the weighted average atomic mass, well, you can use that equation. That's going to be very helpful in this case. So let's go ahead and write that down. So you probably have seen this before. I go over this in other videos. When you want to find the weighted average of the isotopes of a given element, that's basically the atomic mass that's on your periodic table. So you may have been given a problem, which is typical. Hey, find the weighted average of this element, and then here's the isotopes, and here's their percent abundance, and here's their masses of each isotope, and then you plug it into the equation. What equation is that? Well, it's this one. So you have the weighted average, or the atomic mass, if you will. So you have the atomic mass of an element, and that's going to be equal to the percent abundance of, let's say, isotope number one. I'll just say number one. That's, we're talking about isotope number one. So percent abundance of isotope number one, that's going to be multiplied by the mass of that isotope, right? So they usually give you that. So the mass of isotope number one. And then you're going to add to that other isotope. So the second isotope, you'd add to that the percent abundance of number two, isotope number two, multiplied by the mass of number two, right? And so on. You keep going. So whatever number of isotopes you have, you do that for each isotope, right? So percent abundance multiplied by the mass of that isotope. So isotope number one plus abundance, percent abundance, and mass of isotope number two, plus the percent abundance and mass of isotope number three, and so on. And then you add that together, and you should get the weighted average atomic mass of your element, and that should be pretty darn close to what's on the periodic table. Okay, so why is this useful for us? Well, they're giving us two isotopes, and they're giving us the mass, but the masses here are in molar masses, but that doesn't matter because remember, molar masses and atomic mass are pretty related to each other, and they're basically going to be the same number. So for chlorine 37, if we are given this could be in AMUs, atomic mass units. If we're talking about one atom of chlorine 37, then the mass of that is going to be, 36.965 or whatever. So this number here, but in AMUs, right? So a lot of times they'll give you that mass And so here, they want relative abundances of the two isotopes. So, but here we have percent abundances. Well, how are percent abundance and relative abundance related to each other? Well, this is how. You have to understand how to get a percentage, right? So a percentage is going to be, generally speaking, a part divided by a whole multiplied by 100 gives you the percentage. If we're talking about abundance, percent abundance, basically what you're thinking about is we have all of these isotopes, right? We assume 100. And if you have a certain number of isotopes total, and you want to look at, well, okay, well, what's the percentage of one isotope out of the whole, right? So if I wanted the percent abundance of Cl35, well, I would like count out, I get a sample of these atoms of chlorine, count out how many Cl35 I have, count out how many Cl37 I have, take each part that I count out, divide it by the total that I have, multiply by 100, and I get the percentage. Okay, with me so far? I hope so. So if I have the percent abundance, this part here, this part over whole, that is the relative abundance. So you take the relative abundance, multiply by 100, you get the percent abundance. Okay, well, how do you get the relative abundance from the percent abundance? Well, if you multiply by 100 if you multiply the relative abundance by 100 to get the percentage, then you got to divide the percentage by 100 to get the relative abundance. So this is relative abundance. Okay, and so here it would be multiplied by 100, and you get the percentage. If I wanna solve for this, then I would divide both sides by 100, right? And then I have relative abundance by itself. And then that's going to be equal to whatever the percentage is divided by 100. Okay? So then the relative abundance is basically a fraction. So it's a fractional amount of your whole or your sample, if you want to say. Like, what fraction of the whole is going to be this amount, or what fraction of the whole is going to be the Cl37? What fraction of the whole is going to be Cl35, chlorine 35? So that's kind of what you want to be thinking about. Sorry about that. Okay, so where do we go from here? So if we think about this, then basically to get the equation we want, we just take this, and this is going to be divided by 100. If we divide this by 100, we're basically dividing this by 100 to get our relative amount. So what does that leave us with the equation? Let me erase this. So we can, instead of using percent abundances, we can just use the relative abundance, because they're related to each other by 100. So then the equation would be the atomic mass is equal to, and then you could have the relative, I'll just shorthand, relative abundance of number 1 multiplied by mass number 1 plus relative abundance. Oops, let me do this shorthand so I have more space. So relative abundance number 2 times mass number 2, and then so on, just like before. So we can use our equation here. Instead of using percent abundance, we can have relative abundance like this. And so we can begin with that. So why is that? So one of the things you have to do here, one of the things I forgot to show here is that the equation is not complete until you divide by 100 here. So to get the atomic mass, you would multiply the percent of isotope number 1 by the mass of isotope number 1. Add to that the multiplication of the abundance, percent abundance of number 2 by the mass of number 2, and so on. And then you would take all that, divide by 100, and then that would give you the atomic mass. But as I was showing you just a moment ago, taking the percentage and dividing by 100 gives you the relative abundance. So you've got the relative abundance there. So all you need to do is divide the percentage by 100, and you've got the relative abundance. So now all we need to do is, in this case, we don't know the relative abundance of both of these. So we got 2 unknowns. So we're going to need 2 equations. Here's one equation. We need another equation. So the thing about relative abundance is, you know that percentages add up to 100, right? Well, if you divide 100 by 100, you get 1, right? So if I take these percentages and add them up, all the percentages should add up to 100%. But if I divide each of the percentages by 100, then I have to divide the 100% by 100, and that equals 1. So that means that the relative abundances of each isotope should add up to 1. In this case, I only have 2 isotopes. Isotope number 1, I forgot to put the 1 there, and isotope number 2. So what we're going to do is we're going to say chlorine 35, we're going to call that the relative abundance X. So the relative abundance of chlorine 35 is X, and we'll call the relative abundance of chlorine 37 Y. So there's our variables, so X and Y. So anytime you have 2 unknowns or 2 variables, you need that many equations. So we have one equation here. We need another equation. As I said, if these are the relative abundances, the total of all the relative abundances of all your isotopes should add up to 1. So then our second equation is going to be X plus Y equals 1. So there's our second equation. Here's our first equation. So now we can kind of solve this for the abundances. There's just one more thing that we need, and that is the atomic mass. And we're going to need that. Since we have this in molar mass, we're going to put that in molar mass. So if you look on your periodic table, look up chlorine. Depending on what periodic table you have, mine says 35.453. 35.453. So we're going to put that in here. So we're going to put 35.453. 0.453 grams per mole. That's the atomic mass from your periodic table. So let me just make sure I wrote it down correctly. 35.453. Good. So that's going to be equal to the relative abundance of isotope number 1. We're going to call this isotope number 1. So that's going to be X multiplied by the mass of isotope number 1. And that's what we have here. So then we're going to multiply that by 34.96885. And that's grams per mole. And then we're going to add to that the relative abundance of the other isotope multiplied by its mass. So the relative abundance of isotope chlorine 37 is going to be Y. So that's going to be Y. So we're replacing this with Y. Y times, and then the mass of the isotope number 2, again, chlorine 37. So 36.96. So 36.96590. And that's grams per mole. And so there's our equation with our X's and Y, relative abundance of chlorine 35 and chlorine 37. So now we have two unknowns here. We have two equations. What we need to do is solve this for one of the variables and substitute. So let me see what I did here. Make sure I got the right one. So I'm going to solve for Y. So here, if we solve this for Y, Y is equal to, so we're going to bring the X over, so negative X or minus X minus X. So then Y becomes 1 minus X. So now that we know that Y is equal to this, I can take Y and I can substitute this in for Y. So then my equation becomes 35.453 grams per mole is equal to X times 34.96885 grams per mole plus, and then I'm going to substitute this in for Y. So it's going to be 1 minus X times 36.96590 grams per mole. Okay, I think you probably see where I'm going with this. So now that I have X, now I just solve the equation for X. So keep going. So I'm going to multiply this through this. So I'm gonna multiply this to these two in here. So I'm gonna expand it. So I have 35.453 grams per mole equals, and this will be, I'll put the X on the other side, or we could just, yeah. So I'll have 34.96885 grams per mole times X. All I did was I switched those around. I didn't really need to do that, but normally the numbers in front of the letter or the variable. So I'm just changing it to fit that form. And then this, this is multiplied by 1. So this times 1 gives me this back. So that's going to be 36.96590. And that's grams per mole. And then it's just this times negative X. So that's going to be minus 36.96590 grams per mole. And again, that's going to be multiplied by X. So now I have everything kind of expanded out. So now what I need to do is get the x's together. So I'm going to add these two together. And I'm going to have to bring this. This is without an x. This number here, I can bring over to this side. So we can add these two together. But let's subtract this number first. Let's do this step by step. So I'm going to subtract 36.96590 grams per mole. And then I'm going to subtract here 36.96590 grams per mole. And when I do that, I get over here negative 1.5. So negative 1.5. Where's my other number? 1.5129 grams per mole. And then that's equal to these two. So I'm going to take this x and add it to this x. When I add these two together, right, I get, what did I get? Negative 1.997. So we're going to have negative 1.99705 grams per mole times x. Okay, so now all I need to do is divide both sides by this number here. I would need to get x by itself. So I'm going to divide both sides by negative 1.99705 grams per mole. Divide this side by negative 1.99705 grams per mole. So this cancels out. Here, grams per mole cancels out. And then when I take this, I divide these two numbers together. X then equals what do I get? 0.7576. So x equals 0.7576 for the relative abundance. Notice that the relative abundance is a decimal, right? That's a fractional amount. If I was to multiply this by 100, then I get the percent abundance. So if I multiply this by 100, I get 75.76%. Okay, so this is the fractional abundance or relative abundance, right? In a fraction, this is the percent abundance. Okay, and then to get the and this would be the fractional abundance or the relative abundance of chlorine 35. So because we said chlorine 35 was X, so chlorine 35 has a fractional abundance of 0.7576, and that goes to 75.76%. And then all we need to do is take this number and plug it back into our equation here. So, or actually this one here. So if we take x and put it in there, we subtract x from 1, and what do we get? If we subtract x from 1, we get y is equal to 1 minus 0.7576, and that gives us, what did I get? 0.2424. 0.2424. So then what we do is we take this. So this is y. So we'll write that down here. Y is equal to 0.2424. So that is the relative abundance of y. And again, if you multiply that by 100, you get the percent. So if we multiply that by 100, we get 24.24% abundance for X and Y. And again, X is chlorine 35. So I'll write chlorine 35 here. So that is the relative and percent abundance of chlorine 35. And this is the chlorine 37 isotope. And so that, ladies and gentlemen, is how you would solve this problem. So just remember, the key here is if you know this equation, you have to remember that the percent abundance divided by 100 gives you the relative abundance here. And so that's kind of hidden in the equation because you got the percent abundance and you got the 100 here, because after you add everything together, you just divide it by 100. But they don't usually tell you that, hey, when you divide the percent abundance by 100, that's giving you the relative abundance. So then the equation is just simply atomic mass equals the relative abundance multiplied by the mass plus the relative abundance multiplied by the mass plus the relative abundance multiplied by the mass. And again, the relative abundance is just the percent abundance divided by 100. And so that's it for this video. I hope this was helpful. If this was helpful, or if you enjoyed the video, or both, please, by all means, like the video, share the video, hit that like button somewhere over there. If you have, oh, by the way, don't forget to subscribe to my channel. Hit that notification bell. When you do, make sure you click all so you can be notified by all the videos I put out. And then finally, put a comment down below in the comment area. Make sure that you ask me questions. Let me know what you think. If you have a problem or a question you want me to help you with, or if you have a topic you want me to cover, I would love to do that for you. Thank you for joining me, and have a great day.